So let's start. Again, if there are any questions, please interrupt, and I'll be happy to answer if I can. So I'll now share my screen.
Like usual, enter indexing data. You do the git pull to get to the new release of the exercise, and then the rsync. And be sure that you have the right version that Pieter is showing. So the file is called, you can see in the top, pygeo_pktools. And is always under the usual exercise folder. It should be quite straight line. You open, anyone see if they can open? Ah, right, they need to give the, yeah, okay, perfect.
Thank you. Should I wait a little? Do you have all these the notebooks open, or you need some help? Because I think you have more. It's best if you can also type things and try things for yourself. That I think that's the best way to follow.
Yeah, you have also in the under PK tools menu bar in the spatial ecology, you have also this web page as a web page.
Should I continue, or is there anyone that would like some help? Or you want me to wait a little?
Works for me, but I'm just one person.
Yes.
No, I was just saying it works for me. All good on my end.
Ah, it works for you. Okay, so no need to wait for you. Someone else?
It works for me too here. Thank you.
Okay. Great.
Okay, I think so we are in a good go. Yeah.
Yeah, it works.
Good. Great. So let's start with executing the first cell. So we're just importing some libraries. Pathlib is for so working with paths, and the nice thing about this package, it works. We're in a Linux environment here, but the Pathlib works with different operating systems, so it takes care of the backslash and the slashes if you would work on Windows, for example. So it's quite a nice. I'm always using that if I'm working with file names and paths. Then NumPy and Pandas, we're importing Matplotlib for showing some figures, and then Pygeo later on in a few cells also, of course, we'll need. But first, I would like to go through the same examples as Giuseppe has shown with PK tools. For example, the first one was to create a mask, and he was using PK get mask for that. And as you see here, the three lines, they're opening an image with a -I here, so each time the same image, and then writing three different masks with a threshold A, B, and C. So we're getting three masks in file format at the end. So it for a minimum of 1 and a maximum of 2, a minimum of 5, a maximum of 8, and then a minimum of 0 and a maximum of 10. So the three different masks we get. However, if we can do this with Python in a similar way, but a bit more Pythonic, by creating the masks as follows. The mask 1 is if Jim is larger or equal than 1 or smaller than equal than 2, and the same for mask 2 and the same for mask 3. So this is very similar as the get mask you saw here, but now everything is in memory. You have 3 masks as gem files, gem objects, sorry, that are in memory. And then we can apply these as we were also doing with PK tools. Later on, we will see that we don't actually have to go through this. This was just showing and in a very slow way that we can go from PK tools to PyGeo, but we'll see later on that it's actually much easier than what I'm showing here. But just following on, the PK tools was then setting these 3 different masks, and we can do similar thing here with the 3 masks. We set a mask, a raster mask on gem, so every pixel in mask which is above 0, which has 1 as a pixel value, will be set to -9. Every pixel value that is above 0 in mask 2 will have its gem pixel assigned to -5, and the same for mask 3, we will assign -10. So we can do this, and then gem will be set accordingly, So now gem will be the same as we have done with PK tools, but now we are with entirely in memory. However, if we start over again, so we just clean, or we start from scratch, we open the gem image from this file name you see here. We open that image and we create the different masks on the fly. Here, the first one is negative values or values above 10. We will assign a value -10, and then between 5 and 8 will be a -5, and between 1 and 2 will have a -9. You see that in this case it's important. The order is important, because if we would start with this value, then it would change the output. So you see that it's in this case it's quite important that we follow the order as we see here. What we can do then is to actually check if the results are the same, and to do that I would like to give this as an exercise. So can you please check in PyGeo using the tool isEqual from the properties, that the gem we obtain after this cell here is actually the same as the mask, as the set mask we obtained with PK tools. So here the output will be this file, and I would like you to check if this output here we have written is the same as our gem object we have here in memory. Any questions for how to do that? If you go to the PyGeo documentation, and I will share again the link here with you, and also hold on. This is the general link, and then there is a specific function called isEqual. That is part of the properties module. Is the exercise clear? Yeah. Someone has the answer yet?
I get a false, so I must have done something wrong. So I'm not done.
Sorry, I didn't get that. Say again.
I got a false, so I must have done something wrong.
You have a false. Okay, interesting. Good. So let's. Someone else has another result. Someone has true.
Yeah, I got true.
You have true. Okay. Can you tell us how you did it?
I just created a new file name object with the output file. Then I read it in as another gem, and then I used the gem we just created with PyGeo, and the dot properties dot is equal, and then in brackets just the new gem I created.
Okay, perfect. So let's do it here. Then you can also check if those had a different result. So first, what we can do is create a temporary gem. We call it gem0. We say this equals pj.gem, and then we'll use this file here. That was the output of the PK tools. Once we have this, we can say, is this equal to our gem? Sorry. That must be in bracket, of course. So this is true. If another way how you could also do it, so in this case we're creating a temporary variable gem0. Another way doing it would be to start with, let's say, gem properties is equal, and without creating a temporary variable gem0, we can just say here, this one is also a gem. So we open the gem here, and this will result in a gem, and we check if this is actually the same as our gem. We have the same. Is that clear for all?
Yeah, Peter, one question. The second case,
sorry,
in the second case, is both the both the image in the RAM before to compute the true and after?
Yeah, that's a good point indeed. So we're not instantaneously the image is created also in memory. So the memory footprint will be there, of course, but because it has to read it in. However, the garbage collector will get rid of that memory if it's needed. Whereas if you keep the gem0, it will drag it all along to the end, and the memory footprint will stay. Whereas if you have, for example, a garbage cleaner, you could even force the garbage cleaner of Python to say, now I want it to be purged, I don't want it anymore. Or if you run into memory problems, it will see that you're not using this as a variable anymore, and it can get rid of it. So there is a difference indeed. But if, for example, you're reading a huge image of 10 gigabyte and you only have 2 gigabytes of memory available, then it won't work, because at least you need it to read it. Correct.
Yeah, thank you.
Okay, and then of course we can also save the result as we were doing here, and here we use the same type of creation options. We say gem.io.write, our file name, and the creation options here. So it's a bit of a different syntax as we were doing here, but it's quite easy to understand, I think. Okay. The next, are there some questions, other questions here? No. Okay, good. Let's continue then with the next step. The next exercise that Giuseppe was doing with PK tools was to composite images. you for those who might not remember what compositing is a step where you have several images stacked, because, for example, you have been acquiring images over a full month of the same area, and some of the pixels just overlap, and then you create a single image that computes according to some kind of rule how these overlapping pixels should be combined. You can take either a maximum of those, or you can take a minimum or a mean or a median, the standard deviation. There are different ways of rule or different rules you can apply how the composite should be created. So there's a difference between compositing, which is handling overlapping images, overlapping pixels, or mosaicing. Mosaicing is rather if you have if you have patches of different images that are not overlapping but are near to each other, you can create a bigger image that is that has the bounding box of the largest extent of all those. So that's a bit of a background. So what we're doing here is to composite. In PK Tools, we first created a mask because we wanted pixels below 0 and above 25 to have a value 0, and all between we wanted to retain those. So this is first a mask we are creating, and then we are creating actually two composites. One was a composite for the mean, to calculate the mean, and the other was the composite to calculate the standard deviation. It had to be done in 2 steps because the composite was only able to create one rule at a time, and one rule here, the first was the mean and the second was the standard deviation. So for all these different images we have, we'll composite those, and you see here that all the images, they are all the monthly images, one image for each month that we are stacking and then creating the composite for. An alternative way to do this also in PK Tools was, first of all, to create a virtual file which was actually stacking all those in a single VRT file, and then calculating a statistic profile with the where you can actually have multiple rules, so you don't have to go over twice. You can say calculate the mean as a function, the standard deviation as a function, and put the output in this file here. So this was the way it was done with PK Tools. So let's see how it's done with PyGeo. We have seen already, I think it was on Wednesday, that there's this function of the geometry module which is called reduce plane, and as you remember also what in a PyGeo gem object, it can deal with overlapping images by having this concept of a data cube. So we will first load an entire data cube containing all the different months in one gem object, and we will also create a mask, but the mask was based only on the very first month, if I remember well. So we want to create the mask only from the first month, but then stack all the different months in one data cube. And so this is done in this part here. So what you see here, we are using two different files. One is because the file names are named as 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, 11, 12, I believe, for the last 3 months. And what we do here is we create an empty mask as an empty gym, which so all the values, all the pixel values are 0. We create an empty gym, and actually for the actual gym data cube we will fill in later. So at this moment it's not all it's just an empty box. There are no pixels, there's no dimension, no geometric information, so this is just an empty gym which doesn't contain anything. But we're going to fill it in, and so this by first of all looping through all these files. So the two files we have defined here, if I say for file in this first list from 0 to 9 or 1 to 9, and then 10, 11, 12. For all these files, we're going to read in that image, but actually, so you see here the way I was doing also with is equal. I'm reading the file here, but I'm not creating a temporary variable, a named temporary variable. I'm just reading the file here and directly stacking that as a new plane to first my empty image, but once it's filled in after the first iteration, it is being filled, and the second will go just on top of that. Know that all the files we're reading in here, they have the same geometry, the same projection, the same number of pixels, lines and columns, and this is needed if we want to stack the different images together. What we also do here is we're going to set the dimension, of the plane. So reading in a plane, and we are naming that plane, we're labeling that plane as the date we read it in. So there is a month that we read in, and we are going to assign a label being that the first of that month. The first is just arbitrary. I just ended it's 2019. Maybe it's not correct, but I was assigning a real date to each of those planes, and we'll see later on how we can also use that. Once all the files have been read in, we will also set the dimension for the band. So we also label the band, and we know that those bands are actually LST, so we'll name that also accordingly. If you have executed this cell, what I would like you to do now is to, as an exercise, is to use the X-ray representation of Jim to display the details on the dimension and the variables and the labels of that object. So you see that we have actually labeled these. I can show you here, for example, if I say Jim.properties get dimension, we will get a dictionary with, on the plane dimension, we have all those 12 months, and we have a single band image where the band is being labeled as LST. Now I would like you to use the X-ray representation to see actually more details on this object. Someone has done it already?
Sorry, was the exercise just to convert it to an X-ray?
So yes, so you create an X-ray from the Jim object, and you just display that X-ray. So, and then you see that actually there are some attributes you can visualize in that cell. Let me copy this. Here in the chat, I've pasted the documentation so you can see how it's done. Let me know if you need me to continue. If I'm going too slow or too fast, then it's important for me to know that you're not. I can imagine that it can be frustrating if you want to do it yourself and then I'm already showing the result, but it can also be frustrating if I'm waiting too long, that you are bored. So it's difficult for me, especially if it's not a live session that I'm there and I can see, I can walk around. So and I just have to rely on your feedback to know how fast to go.
Yeah, that's tricky as a lecturer. I'm actually, I think I have a wrong version. I just did a git pull, but I don't have the date in the cell that we just did.
You don't have the date?
Yeah, like you extract, or is this further down? No. You extract the date and the name, label the planes. I don't have this part.
So try to visual remove it in the my SE data, that one, and then do the resync, because the git pull will get a fresh one.
So
Okay.
what you mean is you don't have this line, correct?
Yeah, exactly.
Okay, yeah.
And then the 2 lines below either, by where you
And
name
this
it.
one either, yeah, that's quite important, especially if you want to go back and forth to this X-array, because X-array is using these labels, and if it doesn't find the label, I will fill in like arbitrary, or not arbitrary, but I will just like use band 0, band 1, and as and T0 or 1, 2, 3 for the time, so it will be meaningless. Whereas here we actually deal with times, and that's quite useful.
Yeah, I'll download the new one. But to turn it into an X-array, just to add to that, is just with gym.xr parentheses.
Exactly. Yeah, exactly. So let's do it here. So what you would see is probably if you don't fill those dates in, you will not have the same as I have here. So the nice thing about this X-array also is it shows you actually the dimensions. It has 12 planes, or with a time dimension. You see the number of rows and columns. You see also the data variable as a name is LST, and these are actually the values. And you can even drill further in. If you click on this database here, you actually see a snapshot of the actual data, which is also quite handy. Are you with me?
Yes.
Okay, thanks.
Yeah.
So now let's do this reduce plane, and you'll see that I've written here the commands to see actually what is going on. So first we create, so we haven't created, if I'm correct, yes, so we haven't created the mask here yet, so we are just filling the entire data cube. I've just created an empty mask here, but it was not filled in. So what we do here is we create a mask by cropping, taking the first plane of Jim. So this mask is the first plane of Jim, so the first date, and now we set it accordingly as the same as we were doing in PK tools. We say if this mask, which is actually the first plane of Jim, if it's above 0 and below 25, sorry, it is, then it should be between 0 and 25, it should be 0. We set Jim to 0 if it's between 0 and 25. Once that is done, so we set all these values to 0 in Jim, and then we calculate the reduced plane. This was taking some time. It was relatively fast, but it can be considerably faster if we don't have to take into account this no data value. This no data value is actually rather computationally intensive, because for each value it has to check it, and so it's faster. I leave it up to as an exercise to you as an exercise to check this, how fast it is by creating a new variable, a new Jim object called mean all data, which is doing the same thing but reducing the plane, also calculating the mean, but without taking into account the no data. So also all the data between 0 and 25 will be taken into account. Is that clear as an exercise? Yeah.
Is it possible to, sorry, I have a question.
Yeah.
Is it possible to use NP nans and then have an argument like ignore nans? Is it possible?
Yes, it is possible, but we'll see that in a minute. You have to know that the Jim object itself does not have a none value. It doesn't know about none values. The none values is a typical thing used in NumPy, in Xarray, and also in R. I'm using a no data value that you can set. But what you can do is by using the bridge to NumPy to work with none values, and we'll see that how this can be done in a minute.
Okay. All right. Okay. Thank you.
Yeah, welcome. So here, actually, it's a very simple exercise. You just copy that line, paste it here, and you get rid of this no data. It's finished. However, I did not do the exercise correctly, but because this one should have been called like this, and this means that I lost my mean, so I have to execute this again. And you see actually that this reduced plane is taking longer than it's still not that slow, but it's longer than using this here. And especially if you have many planes and very large images, then it will make a difference. So going back to this question from before, let's see how we can do it with NumPy. So we will execute this cell here by saying, first of all, we create a float data type, and because the none value only works if you work with floats. So that's an important detail. And then because the mask before it was if it's created in this way here, then it's just a byte, because this is dealing with, remember there was a question on Wednesday, like, is a mask when you have this bigger than or equal than, is this a boolean, and I was, or is it a 0 1, and I mentioned no, it's a 0 1 and it's a byte data type. So our mask is a byte data type, but we want it to be float because we're dealing with not a number values. Here we are converting the mask with setting the creating a non-mean, and the non-mean is actually creating is calculating the mean value, but not considering the non-values. So non-mean is a special function of mean where you can deal with non-values. And when you calculate the mean, you also have to say in which axis you want to create a mean, because remember we have a three-dimensional image, and hold on, because I have to check here why I'm using. Okay, so here our gym object you see here, when we convert in a NumPy, was a three-dimensional cube. So now our NumPy array is also a three-dimensional cube, and when we say calculate the mean of this cube, we could take the mean of the entire cube as one value, where you go through all the rows, all the columns, and all the time, all the planes, and then just end up with one value. This is not what we want. We want to calculate the mean only for the very first axis, axis 0, which is our time dimension. So this is another important thing you have to know. When we are dealing with a NumPy array as a representation of our gym object, the first axis is the time axis, so the plane. The second axis is the number of rows, is the row axis, and the third axis, so axis number 2 in this case would be, so the third one would be the columns. So in this case we calculate the mean taking into account or not into account the non-values, let's say, and calculating it in the plane direction, so that we still have a XY direction, a two-dimensional image at the end. We will stack this result on top of our mask we had initially. So our mask was a one-dimensional, a single plane image, and now we have a single plane and single band image. Now we will have two bands, because we are stacking the same mask we obtained over here on top of that, and we do the same by calculating not the mean but the standard deviation. So that's the non-standard deviation if we want to neglect all the non-values. Again, we are calculating the standard deviation over the plane direction, meaning axis 0, and the result of this we are putting into the second second band of our mask. Again, I acknowledge this is a bit cryptic, and I was even not entirely correct when I was explaining it. So I'll start again. Remember that our mask is a floating point, single band, single plane image. We want what we are going to do is once we are just reusing this mask because we don't use this mask anymore after this. We have used it before this mask to set the values to mask our gym image. Our gym image had 0 values where we wanted to mask before. So before we had to mask these, and we use this no data value. What are we going to do here? Our gym image, wherever it was 0, we are putting a nan value. Okay. Then what we are doing here is we are calculating first the mean value over all this times all the planes of gym, and we're setting that in the single plane, single band mask value. So we override the existing values of mask. Then we are just replicating that same image, so as a new band of our mask. So after this stack band, we will have a single plane but 2 band gym object, where the second band is just a replication, just a duplication of our first band. So now we have, after this, we have 2 bands, and we are in this third line, we are going to override the second band of our mask with the standard deviation. And how we are going to access our second band, and this is the one you see here. So if we want to access our second band, we are accessing it through this number 1 here as a parameter of the NumPy representation of our gym object here. Are there any? I can imagine there are some questions.
Yeah, yes,
Hello.
there's actually one in the chat. Maybe
Hello.
In the chat, let me check the chat here. Hold on. A question. AA. I cannot see. Do you have a question, AA? I don't know who you are.
Adigun, I have a question. Yes.
Hello, Adigun.
I want to get the concept of the plane right. Now, you are just like if you have an image, the X and Y. Now, like if you have a value for temperature, then is that the thing you are referring to time? Like if you have your longitude, latitude, and you have a value for temperature on the image, is that your time component?
So I'm not sure if I understand the question. So you have, let's say you have a 3-dimensional image. One is the X, one is the Y, and one is
Exactly.
for the temperature.
The value for temperature, you know, the value for the temperature is like the 3rd dimension, if I understand your concept very well.
Okay, but it could be like, is the temperature represented in your pixel? So it's a temperature at one time, that at one specific time, or do you have multiple times for each time a different temperature?
No, at a specific time.
Sorry?
At a specific time.
At one specific time, then we
Exactly.
only have one plane and one band, because you have a 2-dimensional image, and
Yes.
for each pixel in that image, you have one temperature.
Yes.
Suppose you have 2 times one for today and one for
Yes.
yesterday, then
Yes.
you have a two-dimensional, you have a three-dimensional image, because then for each pixel, you have a time for yesterday, a temperature, and a
Yeah.
time for today, a temperature. So this one could be like a cube where you have a time dimension, and we would represent that with two different planes.
Okay.
Is that
Okay. Okay.
is that clear? There's
Okay.
you can also, another way you could deal with it, and that depends on how you want to. You could also say, I want two different images with two different bands, where one band is my temperature and my second band, one band is my temperature at day 1, and my second band is my temperature at day 2. As we were seeing here, when we were reading in the image, in this case, we were stacking them as planes, but we could have stacked them as bands as well. But that depends a bit on the application and what you want to do with it. In this case, if your goal is to create a composite where you combine the different times, then you better create them as multi-plane image rather than a multi-band image.
Okay. Okay.
Okay.
Okay.
Some other questions on this 3 lines here. Is this, or this entire cell here, more or less, has this been clear?
It's been mostly clear. Also, just some clarifications.
Yes.
If we would have, so we have X, Y, and planes. If we would have multiple variables, I forgot what the bands. If we would have multiple bands, would that be axis 3 or 2? Sorry.
Well, in this case, you mean accessing through NumPy array?
Yeah, exactly. Yeah.
No, actually not. This is something that is not supported here. So in our case, it would be a different band. But as you see here, the way you access the band with NumPy is by this number here, this 1.
Yeah. Yeah.
So indeed, it is not possible here to say, I want, let's say I have a 4-dimensional image and I'm accessing the 4-dimensional image here, and I say the axis will be 3 here. That is not possible.
Okay.
So it is only possible here in PyGeo to go from one library to the other, using this bridge, working with 3-dimensional images. I don't support 4. If you want a 4-dimension, I support this in a way with this bands, but you cannot have like a 4-dimensional image that you can play with the way NumPy is doing it.
I see. Thank you.
Okay.
That was my question.
What you could do is probably go entirely in the NumPy world by first creating a NumPy from a gym, and then a second NumPy from another gym or from another band, and then combining these two NumPy arrays in a 4-dimensional image, which is possible also, and going that way. But then I think it's a bit beyond PyGeo, because then you're really dealing with NumPy, and then you can further. What I try to show here is how you can bridge to NumPy and all the things you can do. But this is a bit beyond what the capabilities. Then we're a bit further than what is directly supported by PyGeo. Okay. Yeah.
Thank you.
Welcome. So, any other questions? No. Okay. So let's see how to move on. One thing we could have done is to avoid. One thing we do now is remember that we can have some we will have some another number values in our pixels here, because everywhere where there was another number as a pixel, it will have it can have, or where all the pixels were for all the times where not a number, we can have still another number at the end, and so we can reassign them to a value 0. So, and this is the way we do it, because as I mentioned, in PyGeo, most of the time we want to use no data and not the numbers. So not the number is really dedicated to NumPy arrays, and so this is in this way you can reassign these nums to 0.
Sorry, I had another question actually on the previous cell. Just a clarification. The fact that we're overwriting mask, now it's not really a mask anymore, right? It's just the name of the object, because it's really the mean composite, right?
Yep.
Okay,
correct.
cool. So it's just a leftover name. Cool.
No, very, very good observation. So that's true. So the reason why we're doing it is actually to reduce the memory footprint. So
Yeah. And we keep all the geo information of the mask. So.
Yeah, because that's one of the downsides if also of these notebooks, but also if you are keep on recreating new variables and never going to purge them, to delete them, you will just increase and increase and increase all your memory, and at some point you might run into memory problems. So this is a way to reuse the same variable name, but then just overwriting those pixel values. Yeah.
Excellent, thank you.
So another even better is to avoid the duplication of data and reducing the memory footprint. And so what we're doing here is we're saying we are doing this operation here as we were doing before, but we are actually not copying any of the values. So it will be done in place. So our gym object will also have, we are calculating the non-mean as before, but the result will be in the gym object itself without an extra copy, and then we are assigning all the non-values to 0, and this will then be copied into mask. So it's actually combining the two steps from before into one without creating an extra variable, and that's because of this copy equals false. Here we're going to use the NumPy arrays, also this NumPy representation, to show the images. Again, here, remember that in the mask, we were abusing this mask variable by overwriting the pixel values and having actually two different bands. The first band meaning the mean, and the second band being the standard deviation. And here we're going to write in the first column, we're going to write the original gym image. In the second, the mean value over all the months, and in the third column, the standard deviation over all months. And you see here, to get the standard deviation, we access the second band of this mask, which is converted into a NumPy array, and we show it in the third column here. And we do that the first the first band, it's accessed by this 0, which is, by the way, the same as we would do without. If you see this formulation, this notation NP without any argument, it means take the first band. So this would be the same as taking just 0. Okay. Here, why can someone say what is being done here? What are we showing here in the first image? We are showing the gym image. Why do we do this syntax here? What is actually shown here?
Maybe that you're just showing the first axis and leaving the others blank.
Yes, say that again, please. Yeah, that was correct, I think.
Maybe that you're just showing the first axis and then leaving the other ones blank.
The first plane, no? And then
Yeah.
Yeah, that's correct. So we're remember, as I was saying, the planes is the first dimension. So we're showing here the first plane only, just 0. And then for the other 2 dimension, which is the rows and the columns, this column means take everything. So all the rows and all the columns, but only this one plane. So let me show this in the next here in this cell here. I think we can do this. The gym, if we look at its shape, it has 12 planes, 840 rows, and 1080 columns, right? So if I'm saying I only want the first plane, all the rows and all the columns, I don't have a cube anymore, but I have a two-dimensional image. Similarly, I can take all the columns, but only a single row in this way. And I have all the 1080 columns, but only a single row and a single plane. Or I could even say I want the first to the 10th row and the first to the 10th column of the first plane, and then I have a 10 by 10. Or I want first 2 planes, first 2 planes, and if NumPy array of 2 planes and 10 rows and 10 columns. So this, if we wanted to show here the second plane, we would have done it this way, and then this would be a different image for the month of February instead of the month of January. Okay, all clear?
The syntax is clear, but why do we have to do it like this? Couldn't we also do x1.im show gym.np and then have the 1 in the parentheses of the np and get the first plane like that?
I'm not sure if I was.
Oh, sorry, those are, I'm mixing up my planes and my bands.
Yeah, correct. Yeah. No, it's good to ask a question, because then you know exactly, because it's an important difference indeed.
Yes.
Yeah.
So in the parentheses, we query the bands, and the planes we query via the NumPy dimensions.
Yeah, exactly. So very, very good you mentioned this. So here, because this is, do you see when I highlight this?
Yes.
Yeah. So this actually is a 3-dimensional cube.
Yep.
And this is another 3-dimensional cube from our second band.
Yes.
So each band is a 3-dimensional cube. So what I do not have, I don't support, another way to do it would be a 4-dimensional cube where the bands is another dimension.
Yeah.
But I don't have it. I have only a multi-band, multi-cube. Sorry, a multi-band cubes.
Yes. And
Yep.
the reason why we don't need the square parentheses for x2 and x3 is because they only have one plane each. So that's already taken care of.
Can you ask? I'm not sure if I follow. Say that.
Yeah,
again.
sure. So in the line x2.im show mask, we don't have the in the line above. After that, we have like the square parentheses, right?
Yeah.
Where we query the dimensions. We don't have this for x2 because they only have
exactly
one plane, so we don't have to do it.
Very good. What I could do though, I could do this.
Yes. Yes.
That would have been the same result.
And if we don't, so in the AX1, if we don't query the first plane and try to plot it, does it plot all of the planes or does it just break?
That's a good thing. I don't think it will work because it will.
It's an error.
How can it show you a cube? It's not so easy to show a cube.
Yeah. I thought it might default to like print them all, but so we'd have to write a loop and plot them all separately.
Yeah.
Okay.
So actually, it's trying to do something, but it's kind of stuck. I don't know what is. Shouldn't have done it probably, but very good observation indeed. We'll see how we can deal with it in X-ray. X-rays, it's even more powerful because it takes all the benefits of NumPy arrays and it has a labeling. And it deals with these things, as we will see here in a second. So again here, let's see how we can do these things in X-ray. We create an X-ray as in the way you all know. So our GIM is a 12-time image, so with 12 planes. And the 840 rows and 1080 columns, and it has the LST variable. So what we can do with this X-array, first of all, the syntax is a bit different, although I think this where also is supported by NumPy. It actually comes from the NumPy world as well. So what we do here is we say, I want this X-array here, but I concentrate on those pixel values where this X-array is not 0. Remember, we masked all the 0 pixel values. And in this, when we say, I want only the non-zero pixel values, what this X-array is doing in place, it will assign all the 0 values to none, to another number. So the result of this part here is nothing else than an X-array where all the 0 values are none. Okay? Then on this result, we are calculating the mean value. And again here, remember before we were saying mean and then an axis. In the NumPy world, we say mean and axis 0. Here we say, because our axes are labeled in X-array, we say I want to calculate the mean over the time dimension, and I want to skip the non-other number values. So it's a very similar thing as we saw before with the NumPy array, but now we say, I want our GIM as an X-array. I want to convert the 0 values to none in this way using this where statement. Calculate the mean, instead of non-mean as we had before, we say, no, it's just the mean, but it has an extra parameter, skip, not a number, is true. And we can do the same for the standard deviation. Is that, these two syntaxes, is that clear for everyone?
Yes, actually, they're even easier than before.
It is actually nicer indeed. And especially because we are dealing also with this labeling of the dimensions. It's much nicer indeed. It's taking some time though, but it's quite powerful, because you can take the mean in any dimension, skip another number, and do everything in one line. And then, hold on. Okay. Still calculating. I think what's happening in on my laptop here is that I run into memory problems, and I think I'm using some of the swap disk, which is why it's taking that long actually. So maybe it might be faster in your case, because when I look at my resources, it seems that it's quite heavily loaded on my system. But hopefully getting better already. Also here, I can already, while it's calculating, I can already explain the next part here. So here you also see the way the syntax is formulated. We create an X-array, and instead of saying I'm taking the first time or with these square brackets, here I can say select the first time, then select the variable LST and plot that image as a grayscale image. So this should correspond actually to what we see here. Is it going as slow in your computer than is it this in mine?
No, mine finished.
You're finished already, yeah. So I think it's my computer that is has some difficulties. Maybe I should try to restart the. So you see, and again, here the nice thing about the X-ray also is that it actually showed the geo information, because the NumPy doesn't have a clue about the geo information. It just showed you the number of rows and columns. But here it shows you the actual time, the legend with the variable name, and the X and Y in geographical coordinates. So that's quite nice. And then we do the same for the mean and the standard deviation. While it's calculating, what I would like you to open in the next tab is the link I've shown here. It's actually a very nice website on digital data cubes that is also working with X-rays, and it shows in particular how to deal with time series of remote sensing imageries, and I think it's very well explained, and so the next few cells we're going to see here, they're making use of some of the things they explain very well over there. So in the first one is remember there was this question of can we just plot them all, not just as the first band here, but the second. And I said, well, it's quite difficult. How should the system know how to deal with this cube? How can you show this cube? Well, actually, X-ray has a way to do it, and so it is done here. So we create an X-ray from all our 12 bands, 12 planes. We grab the LST variable of it, and then we plot all of them together. So we're not creating or selecting a single plane. We plot the entire number of planes all the times, but we say treat the time as a column in your plot and wrap it every 6. But we have only 6, so there will be 6. So we have 12. So, but we will only have 6 columns. So this is a way we can show the entire data cube for all the 12 months. So actually, there's it's not something that is all implemented by X-ray, of course. So under the hood, it's all the same things as we have seen here. But what X-ray is doing, it's like a wrapper around this NumPy arrays, where you can easily, first of all, access the dimensions with labels, but then also wrapping these things that you create different columns, and so from the different planes that are available. So that's also quite nice.
Could you post the link that you mentioned that we should click into the chat?
Yes, sure.
Thank you.
We can also have a break, Peter.
Yeah, good idea. And I think in the break I will restart the notebook, as it's getting very slow in my case.
Okay, we come back at 35.
Okay, 6:35. Good. Yeah. See you then.
Peter,
yes.
I think also the student do not have the. Yes,
there is,
yes.
Yeah, there is a new version you should be able to pull. That's correct, Giuseppe?
Not yet, because I'm getting some conflict in
okay.
Gate. So
no problem.
I'm sorry.
So for now, it's you have the link in the chat to this Digital Earth Africa. I'm showing here a command to show all the different planes. So the 12 months from January to December in 6 rows. So you can use these or adapt these as you want. But it's quite a nice way of a wrapper defined by this or implemented by X-ray. As the next exercise, I would like you to plot, instead of the 12 months, to create a new X-ray, and that new X-ray has and to plot that as 4 different columns, and that new X-ray consists of the mean of the 4 different seasons in this year. And so this is if you would not have X-ray, it would be quite a challenging task. And the reason why I'm giving this exercise is because you can appreciate how powerful this X-ray is and how easy actually it is to work with time series. And it's not obvious to do that in other with other software. So I know because I had to implement all in the things before it all existed, and it takes quite some time if you don't have tools like these available. So this and this is also you can find actually the answer in this website on working with time series for Africa and much more even. So you can really use this as a reference, as I'm doing also for my work as well. Did you find the right page in on this website where to go to?
I think so. Yeah, there's a group the time series into seasons.
Yeah, correct. So grouping and resampling by time.
Yeah, they take the median, but
yeah. So you can take the median
mean.
or in this case you can take the mean.
Yeah.
And did it work?
I deleted the workbook to do the Git pull, and now I'm waiting on the new Git pull. So I don't have it open.
Okay.
I did the same thing.
Sorry?
I did the same thing. I'm just waiting for the Git pull.
Okay. So I'll no worries. I'll wait a little then.
Yeah, the same thing.
Yeah, you can do the git pull, but I think it's getting the old version. I still don't understand why. So try to do a git pull, but I think it's the old version. And I push it, but it's not getting down. Okay.
So while we wait, maybe I ask a question. This the seasons, is this because the seasons are encoded in this data, or is it has predefined a predefined relationship between time of year and seasons?
Yeah, that it's a second. So indeed, it's looking at the times in this time dimension, and it's taking it on its best effort. So it will take the different months that are in that season. So
and how are the seasons defined?
Yeah, sorry.
How are the seasons defined? Is it like?
So I believe it's like December, January, February for winter. That's one.
Okay.
And then I'm not sure if you would have like on a daily basis images. So suppose you have 365 planes, one for each day, that it would actually be, I would expect it would actually take the real season, like summer starting from the 21st of June. Of course, as our dates only have months, the best effort it can do is just to look at the months, that if the majority of the month in that season.
Yeah.
But this was just an example. I mean, you can there's
Define your
probably
own.
there's still document that you can have also on a weekly basis. You can have even have rolling averages, like a moving window of different days to filter and all these types. There's a lot of functionalities you can do with these time series.
Okay, perfect. You can now do the git pull, and be sure maybe just get that you remove your old file.
Okay, I did it in the old one, and I think it worked.
Yeah, you should get the one with the link, the Earth.
No, I meant the exercise.
Oh, okay, yes.
Give me a sign when you have it and you have it open, so if I can continue. Okay, Eric has the latest version now.
Yeah, you should be able to get the latest version, and
Okay.
everybody be able to click this link.
Very good.
The digital version.
I'm sorry, and should I do this git pull command on the my SE data direction? Yeah.
Yeah, in the SE data direction, home/SE data.
Yeah. Yes. I thank you, but I constantly receive some error message like the following and tracking working tree files would be overwritten and then aborting like this. So it looks like it's like aborting this update, and I don't know why.
1 second. Can you stop the Peter? Can you stop your sharing?
Yep.
Okay, so if you have any problem with the Git in general, so you should have seen this one. So if you go to the virtual machine, okay, you're scrolling down, you have the Git setting. Okay, so every time that you need to download, you do this, okay? And then if there is any problem, you need to remove the SE data. So if you get some, because this is happening when you, by mistake, you do some operation inside to the SE data, home SE data, you create a file or you modify something, you open even a Jupyter notebook, is going to be different from the repository. So the easy way is to remove the full folder and then redo the git clone. and the rsync. Okay, so this is the operation if you corrupt, let's say, the SC data. And actually, I was getting the same error before when I was not able to hit the book. Okay.
Okay, and please could you show once more where to find this this
yeah,
page?
In the typical preparation of SGL.
Okay.
Yeah, the usual one that you use for. Okay. Then scrolling down, you have the git setting that we have this. So we are using these for everybody, and if something happens, we have this. Okay, I give back the screen to Pieter.
Okay, and you will unmute me also?
Yeah.
Good.
No. You get it? No, you're still on mute. Okay, now I think it's fine.
Good.
Perfect.
So I've copied already the solution to the exercise. Feel free to experiment and to group by different times. But what you see here, so I created a new X-array. So be careful. This one is a real. We're now in the X-array world. This one is not a gem object. This is a gem object. I created X-array object, and by calling these functions here, the result will be a X-array object. We can go back to gem from such an X-array object, but we're not doing it here. We're staying here now in the X-array world, and we can plot these 4 different seasons in this way. We call ds seasonal, then the LST variable. We plot the column season. The column is now called season. There's no time anymore because we don't have the 12 planes as times anymore. We have now a new plane dimension which is called season, and we have 4 of them, and we will have each of those 4 plot as a different column. And here you see actually the season here is winter, December, January, February. Season is June, July, August. Actually, this corresponds to summer. This is March, April, May, and this is September, October, November. The reason why you see this in this order is just because I think of alphabetical ordering D, J, M, S. So it's not winter, spring, and then summer and autumn. So it's assigning the season according to the names of the months. Okay, and actually if you look better at what this season is, you see here that instead of what they had before, the 12 times for our gym X-array, we now have 4 seasons, you see, and the same number of rows and columns. Any questions so far?
Only this time.season syntax. I guess it's like in the documentation, right? You'd have to see what else is out there. I'm sure there's like time.week and
yeah, exactly. Yeah, you have many different things. And for that you just have a look at the documentation of X-array, because we are in the X-array world here.
Yes. Okay. Yeah.
Okay, so the next topic is on tiling. So we are back in the PyGeo world here. We have our gym, and we do the same things as we were doing before. Actually, this is just a plain copy of the things we had before, but we are making a function with the def reduce tile, giving as a parameter a tile index. And we have a tile total of 4 and an overlap of 0, meaning that instead of opening our image entirely, which would have been this only, we are now opening that file as a GIM object, but giving 3 different parameters, saying that we want this to open this file with a total number of 4 tiles, so dividing this image in 4 with a 0 overlap in this case, and we're opening actually which of those 4 tiles depending on the parameter we give as the tile index we give as a parameter of the reduce tile function. So if we call this reduce tile with 0, the parameter 0, we will open the file and the first quarter of that image. Is that clear? So I've implemented these tile index and tile total and tile overlap as a way to deal with very large imagery, so that you can reduce not only the footprint, the memory footprint, but you can also use in a cluster or in a multi-core processor where you can assign different tiles of an image to different cores or to different computers if you have a cluster. And what we're doing here is we're going through these 4 different tiles, by each time calling the reduce tile function. The result is returned as a PyGeo image. We're calling the NumPy representation of that reduced tile function and show this in as an image here. So we're going through the first tile, the second tile, the third tile, and the fourth tile. And once they're all calculated, we can show them. What I'm doing here is a bit stupid because actually I'm doing this in series. So sequentially, first the first tile, then the second, then the third, then the fourth. And I'm not even winning in memory footprint because they all 4 are in memory. But this is just to show you that if you have 4 different computers, instead of this for loop, you could just execute this one on one computer, another on another computer, and then so forth until you launch all processes in parallel. Or if you have a multi-core computer, you can do this with parallel, the GNU parallel function, or you can do it just by opening 4 different terminals and launch the different tiles on a different terminal on your computer. If you have, for example, if you have 4 different cores. So you see here that I have 4 different results, but actually it's one big image just divided in those 4 tiles. Is this, do you have any questions on this? So you see what I've done here. I open the image, but give a tile index, and you can do that with all the files. Anytime you open a GIM image, you just say, I want my tile index to be the first, starting with 0, 1, 2, or 3. Tile index is 4 in this case, and you can also, if you're working with filter operations where you need to, when you have a moving filter, then you will probably you will need some overlap. That's why I implemented this overlap. So you can say if you have a moving window of a kernel size 7, then your overlap would be 4. So that you won't have any of the border effects between the different tiles. You can this tile total can be up to as many as you want. You can divide your image in 1024, for example. The only thing is this tile total needs to be a square number, because I'm dividing it in number of rows and columns that is the same. So it can be either 1, 4, 16, 32, 64, and all the way up, as many as you want, but it needs to be a square number. So and then you can call the different tiles by using this tile index. Is the concept clear? Yeah.
Yeah, this is great, Peter. And so the function does also the merging? No.
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 The function
not
does
yet.
not.
Okay.
No. So what I normally do, what you can do instead, a very easy way to merge is, suppose you have these 1024 different tiles, then you can use a GDAL VRT to create a virtual mosaic of all these, and then you can just work with this virtual file as it would have been one big function. So you don't actually need, I mean, you can then still make one by the GDAL convert, or you can even PyGeo, you can use even PyGeo to open a virtual file, and you see it as one big file. So you don't really need to do the merging, because a GDAL VRT is enough to do it.
Yeah, great. And then second question, of course, this one now is running in a single for loop, isn't it?
Yeah.
When you call the function.
So there's no parallelism here.
Yeah. So how you would do it, the parallelization with the library import sub process?
Well, you mean in Python?
In Python.
Yeah, in Python you could do you can have for loops in parallel with Python libraries, dedicated libraries for for parallelizing, or you can create a Python program of it, and then calling Python, then that script.py with a parameter of where you put this tile index as a parameter. This is what I normally do. So I create a Python script, then I call that Python script with as an argument the tile index, and that I can launch on a cluster. Or you can launch that on your computer with a parallel, GNU parallel, or in the different terminals.
Okay, great, yeah.
The next part is on filtering images.
Sorry, one question.
Yeah, please.
It might not be X-array, but so in the plotting, what do these figure add subplot 221, 222, 223? What are these 200s values?
This one here.
Yeah.
This is actually the. Hold on. It is the wait. Then I have to first image, the second image, the third image, the fourth of a 2x2, 2 rows and 2 columns, and the first one 2 rows and 2 columns, the second one 2 rows and 2 columns, the third one, it's to define the place of the images here.
Okay, so it's not 221, it's 221. Okay.
Yeah, it's not 221, it's 221.
Yeah, got you. Thank you.
Okay. This is the library matplotlib. You can find the documentation of matplotlib.
I'm plotting. I do always in R, and that's why I'm not too familiar with it.
Okay, yeah. This is the matplotlib is the. I know R is very nice plotting as well, but matplotlib can do quite nice things as well. For the in the PK filter that was shown by Giuseppe here is calculating a mean filter, first using a 10 by 10 dimension kernel, and then using a circular kernel filter. So it's a mean filter, so it will smooth your image. In PyGeo we can do the same. There are a number of filters also implemented, as I was doing in PK Tools. I also implemented those in PyGeo, where you can define actually your own tabs. For those not familiar with filtering, the tabs are actually the kernel you define. So if you want to have a moving window where you average all the pixels within that moving window, your tabs would be one all over the place, because each pixel in that window counts, is weighting the same amount for each pixel. So you just add all the pixels with a weight of 1, and you divide, for example, by the total number of pixels in that in that window, which will give you your smooth result. This is what this filter is doing if you would provide your tabs all once. And this is actually what I'm doing here. So my tabs are a NumPy array of all ones of a 10 by 10 array. For example, I can show you here what this tabs is doing. These are my tabs, 10 by 10 all ones.
And these are the pixel weights.
These are the pixel weights for my moving average.
Mm-hmm.
Okay. The norm is true. We'll make sure that the values are still corresponding to the actual dynamic range. So otherwise, if we just add them all up, we will have very large number in our image, because you will add all the pixels. This norm will make sure that you normalize by the sum of all these, so divide by the sum of all these weights. So you get a real average and not just a sum of all the pixels. This padding means I want to have a symmetric, is to take into account what you have to do with the border values. Symmetric is just making sure that if you are at the border of the image, that you know that you just fill in the same amount of pixels on the right as you were having on the left for your moving average. Otherwise, you would not be able to calculate the border pixels. You can also have a padding of zeros, so that you, in case you want to fill them with zeros, or there's several ways of padding you can see at the documentation what type of padding exists. So we can do that. So it's finite impulse response filter in 2 dimensions. We calculate that on the GIM image with the defined tabs, normalized, and and then I print here also this is just to show what's happening with a single value. So this is not important actually, it was just for testing purposes. So our result will be the mean GIM object, and we can show actually that mean object we have it on the left and on the right. We show the original GIM and the averaged GIM. And so here on the right, you see that this is actually a smoothed version. You don't see as much details as you see in the original image. So the second thing that was done by Giuseppe here, where we were defining the circular tabs, we define, it's not as simple as saying here we want this that tabs equals np ones, so we have to use a function for that. defining this function unit circle here, and it's just to see this unit circle is now a 10 by 10 kernel, but with a circular weighting, and the edges of the beyond our circle are having weight 0. And then we can execute the same function here by calculating mean again, but then now as a tabs we use that unit circle 10. And if we then show it on screen, we'll have a very similar result. Actually, it will be very similar as before. We can't see really the difference unless you would really zoom into and see if there's some differences. What I'm doing here is there are other types of filters beyond. Suppose you want to have different filters, not just the ones by defining your own tabs, but if you would look at the documentation of ND image, which is a module in SciPy, the SciPy library of Python, you see that there are many different filters available already, predefined. And here you, for example, you see a Gaussian filter. A Gaussian filter hasn't got this type of a circular filter or a quadratic filter as here, but the Gaussian will have the tabs distributed along a Gaussian curve. So you have more weight for the center pixel and less weight the more you move away from your center pixel. And so this is, you could either create such a, like I defined the unit circle here, you could define a Gaussian function, a two-dimensional Gaussian yourself with the tabs, but you could as well use the SciPy library and just call ND image Gaussian filter with a sigma, for example, a standard deviation of your Gaussian function of 2, sigma is 2, and provide a NumPy array, which is, so it expects a NumPy array. So what we do, we create a NumPy array from our GIM object and give that to the ND image Gaussian filter. The result will normally be a NumPy array. So, but we can avoid that. We can go from our NumPy array by assigning it to the pixel values of our GIM filtered. So we say first, we make space, we make allocate some space for our GIM filtered by saying GIM filters is a copy of our GIM, original GIM. So the GIM filter is just a copy, but we make that copy in order to be able to assign its pixel values using NP, and then all the values you see here, this a single column here is exactly the same as, would be the same as saying this, for example, having all the different dimensions assigned, but we can do that with a single column here, saying all the pixel values should be assigned to this, and this is just the result of my Gaussian filter. And then and the Gaussian and the image Gaussian filter, we could hold on. I don't know why I'm okay. That's another thing. Here, this is the one way to do things. I'm calculating the ND the NumPy array and putting that in my copy I put here. Of course, this will double my footprint because I have the original GIM, I have an output here, and actually here I have it tripled because here I have my original GIM, I have created this GIM filtered, and by creating this one, a temporary output result will be created, and then I'm putting it here, and only once it has been assigned, at that point, indeed, this one could be deleted. but this ND image also provide a better way to limit the footprint by saying, when you calculate this ND image Gaussian, I want this as input, but as output, I want it to override my same image, so I don't create any temporary image here. The output is the same as my input, and we can see indeed that the gym on which it is operated is used as output is equal as the gym filtered I was calculating here. So at this point, my gym was actually replaced and is now has a new filtered version. Any questions on this? All clear?
Yes, maybe I have a question.
Yes, please.
So in this cell, gym and gym filtered will be the same, right? Because you're calculating the same operation on the two variables. Is that correct, or did I miss something?
Yes. So here at this point, we still had our original gym, which was the non-filtered version, correct?
Yeah.
Here we copy it in gym filtered. So at this point, gym filtered is not filtered yet. It's just a copy of gym, the original gym, right?
Yeah.
Here we are calculating the filtered version of our gym, but gym is not altered. Gym is still original. This is untouched. After this calculation, we still have our original gym, and our result is put in this gym filtered.
Yeah.
At this point, the third line is different. Here we calculate the filtered version on our original gym, but we say that the output, we force the output to be in the gym.np.
Okay. But if we wanted to compare the two, then we shouldn't run the third line.
Sorry, say that again. I didn't hear.
If we want to compare the two, gym and gym filtered, then we shouldn't run the third line. Is that right?
If to be able to run this one, you mean this fourth?
Oh no, I mean to compare them to plot the two figures side by side.
Ah, no, because indeed, if you want to compare them as here, you cannot run it here because at this point the gym is overwritten.
Yeah. All right.
Yeah. After this one, you will have the same images. As I'm still showing here, I am assert that these two are equal. So assert is like saying it can only pass if it is true.
Okay. Yeah. Then I got that line correctly. Thank you.
Okay. Any other question?
Yes, and is it possible also to filter through the temporal dimensions? For example, not to filter through spatial coordinates. Like, for example, we have time series of images and we want to calculate like smoothed time series like this.
Yes, sure. And then we come back to what I was saying before, that it would be, I mean, there are several options here. Either you can do it with NumPy, or you can do it with X-ray. And with X-ray, you can use it all in all the dimensions, but that would be, you would use rolling for that. Oh, let me check. There's even an in-place version there as well. So let me just I'm going to take the chat here. I'm pasting the function here in the chat. You see my message?
Yes.
So this, if you would do, for example, gym.xr and then do dot rolling, you could have dim equal time. And then say the for example, you could even have like dim equals time, but also have like time equals 3 or time equals 5, and then you would have like a mean moving average of 4 or 5 or 7 or 8 kernel size. Is that you know what I mean? Let me check. Maybe we can try it here. The thing is, our gym is now already altered, but maybe I can still do it here. The thing is now, yeah, I only have a single time function here, but we would have something like this. So similar to what we had before with the grouping, instead of grouping and then calling the mean on the grouping for the seasons, instead of grouping, you could say rolling, and then you have you have a rolling function over the time, so where you calculate the mean of 3 different time observations, and the result will then be your averaged over time, or average function over time. Okay. There is also, this is in the X-ray world. There is also if you do it in the PyGeo world, you could have also this one here. So let's, I would like to have my gym back. Okay. Where are we? Okay, now I have my gym back of 12, and where we had here, this one, in the PyGeo, we have a function and instead of filter 2D, we take a 1D and we say our tabs, instead of 2-dimensional tabs, we can have I think it's like this. Let's see if it works. So are what we have done here is exactly what you were saying. We filtered our gym object, but in this we don't have a two-dimensional weighting. We have a one-dimensional because we only go in the time dimension, in the plane direction, and with a length of 3. So here we would calculate the mean value of each 3 consecutive months. You see? Was that Alexander who was asking the question?
Yeah, thank you.
Okay. Other questions? If not, we go further to image statistics. Maybe I have to go a bit faster because there's still some more things to do. Here we have the pk stat function giving a histogram of the UG Bio 3 image. However, we saw here that it's from 0, the minimum is 0, but it's not really very informative because it's all zeros. But if we look at this image here and we concentrate between 0 and 20, then we concentrate on 20 different bins. We divide it in 20 different bins, starting only from value 0. We see that we have values from 0 to 5, and it's distributed in this way. So this was the way we do it with PK tools. In PyJ, we have a similar function. We say we open the image as a gym, and we say get it's in the module stats, get stats with a histogram and with the source min equals 0. And then the result will be in a dictionary, as you will see here. The result will be like this. It's a dictionary of our bins and our histogram, the occurrences. So here I show them from 0 to 10 for the occurrences and the bins. And we can show that also in this plot. We see that most of the values are around value of 80. As you see also here, probably, these are only the first 20 values. So here you see it's all concentrated around 80. Then there is a reclassification. I'm not going to show too much of the how it's done here. Here I wanted to mimic how it is done in PK tools. However, it's this very much simpler notation. In the Pythonic way, we can say we want to replace all our pixel values below 75 by 0 and all our pixel values above or equal 75 as 1, and we can see that it is actually the same as we would do in this more complicated way as it was done here. So it is a very simple way of dealing with thresholds in PyGeo. Then finally, as a last part, I would like to show you how you can extract values. There was a question on Wednesday on the performance. So here it's all about how you can deal with this extraction of polygons overlaid on a raster image. and you're feel free to experiment and see the performance. This is how it's done in PK Tools. Here it's here it's how it's done in also in PK Tools for both means and for this is mean also and standard deviation, mean and standard deviation. But in PyGeo we do it in memory. Here we have a GIM image. We open a GIM image and we open a GIM vector. The GIM vector is this vector here, and we open it in this way. So instead of GIM, we say GIMVect. That's our vector object in PyGeo, and we assign it to a variable v. Be careful if you want to override. It might fail because some of the vector file formats don't like to be overwritten unless you have a specific creation option that you can override. So that's why I'm removing each time before I create it. I'm removing that existing file in case you want to execute this cell twice. So now it should be possible because I'm removing it before executing the extraction here again. But you see here what's happening. The extract function is part of the geometry module. I give as an input the sample, the vector file I was opening here, these polygons from that file. The other parameter is the raster, and then I give also an output where the new vector file will be written, and that new vector file will contain the mean, the standard deviation, and the minimum value of all the pixels that are within that polygon. And I don't want to take into account values -1. Then this was by creating an output of type SQLite, of the format SQLite, so SQLite, Spatialite format. We can also do it using with an output as an Esri shapefile. Then you just say format equals Esri shapefile. However, you can also, and often much better, do it entirely in memory. And for that, you only need to say format equals memory. You also give an output name, but you can do it entirely in memory, and your extracted it's most of the time it's much faster, and you have your vector in memory. There's also here in PyGeo for vectors, there's a bridge to pandas. As I think I've shown that already on Wednesday. So, but that gives you here the opportunity to see what's happening. Here we extracting, instead of one mean or one standard deviation or minimum, we are extracting just each of all the points within that polygon and assign it a different pixel value in vector format. So that will be a point for each pixel. We have in total 22,148 pixels that were covered by these 3 polygons. And so here you see the result. This is actually the pixel value, similar to as was Giuseppe was saying. I think it's like PK info or GDAL info of you can get a specific value for a specific pixel. If you have the coordinates in a vector format, you can have it in this way, and you have immediately the results. You can also say I want here point data, so 1 point for each vector, like it will be then the centroid of each. The mean. It will calculate the mean of all the pixel values within the polygon, and so the result will also be calculated in memory here. So it will be a point output, but we can also say I want to have a buffer where the buffer size equals, for example, the resolution or the resolution of your pixel. So it will be a pixel, a resolution, suppose of 20 meters. Then I will say I want to have 5 pixels, or 5 meters is my buffer. So my buffer will be 5 meters, and around each of those pixels, I want to calculate the mean, the standard deviation, and the minimum value. And here again, so you see for all these 174 pixels defined, I will have the for that buffer the mean and the standard deviation and the minimum. Okay, that was a bit of a rush. Any questions so far for this on this zonal statistics, so this extraction?
In the line where it says extracted to, so it was one of the, yeah, exactly. What? No, above then? That's extracted for.
This one here?
Yes, exactly. So in this one, we are writing the result both into memory and to disk, right? We're writing it to extracted to and to this output temp shape file. Is that correct?
Yes, that's correct. Actually, we are right. It will not be written yet, but the way what I'm using as a data format actually for the vectors, I'm using I'm relying on the GDAL vectors, and I am keeping those in memory. However, GDAL needs a file name, and that file name can either be in memory as we were doing here, or it can be on disk. But when I'm dealing with the vectors up to this point here, I'm doing it everything in memory. Nothing is yet written to disk. Everything is in memory, and it's only written to disk either by forcing this, saying extract to io.write. At this point, it will be written to disk, or if the program is executed at the end and we exit the program, then it will be also written to disk. But at this point, it will only be in memory.
Okay.
And in memory, and then after when we exit or when we force the writing, it will also be written to disk. In this case here, everything is just in memory.
Yeah. And then this temp dot shape, that also, it doesn't get written. There's not an empty file on my drive then.
Where are we?
In the extracted to, the one above.
This one here.
Yes, exactly.
This one will actually, if this one will actually be written, because because here, if we don't want it to be written only in memory, we need to put this O format equals memory.
Yeah. Okay.
Or another way would to be, if you would say here, instead of geodata, you say, if instead of this, you would say VSI mem.
I see.
That's another way, like this would also be in memory. But if you really want it in memory, or another way of putting in memory is also this. But here it is not. It is actually a directory that exists on disk, So it will also be written on disk.
Okay, okay, that answers my question. Thank you.
Okay.
It creates, in fact, 2 copies of this data set, or it just creates or 1 copy on the disk and the link which is in memory, or it's just 2 similar copies of this.
No, it will be a real vector in the format you specify. So it can be an Esri shapefile if you specify O format Esri shapefile, and if you get out of the Python script, it will actually be a real vector file that you can open in QGIS.
Okay.
So there are 2 copies in the sense there's one in RAM and one in ROM.
Yeah, so that's correct. And it allows actually I implemented it in this way because it allowed, by having it in memory, it allowed me also to do it to work with it in parallel. If I work with a pure GDAL vector, which is also referring to a disk file names or a file name in memory, if I would keep it in that way, it does not allow me to work in parallel. If by duplicating in memory, it allows me to have a different format, to reshape it in a different format that I'm able to work with it in parallel. So it's a bit of a price to pay in memory to duplicate it, but most of the time those shape files or these vector files are not as big as the raster files we're dealing with. So that was a price I was willing to pay.
Yes, and if this copy, which is in memory, would be changed somewhere, modified, then it would then differ from the copy which is on the disk. So we'll need to maybe to write to the disk one more after if this file is which is the data which is in memory will be modified.
No, it will be no. At the end, when it it will the one on disk will be then finally the same as your memory.
Okay.
You don't have to deal with that. That's automatically done.
So even if we mutate the file, like in the next cell, we say extracted to, I don't know, make some changes to it, those changes are immediately written to disk as well?
That's a good point. Probably I don't think it is possible even, because each time you change a vector, a gym vect, if you create one or you change one, you would need to set an output. So you would need to set a different name.
I see. So we don't have the option to change it without the output. Okay.
So you cannot say here extracted. So if you would say extract 2 equals another extract here, by changing, you would define also an output here. So you can only work here with extracted 2 by saying properties dot get feature count, which has 3 features. So you can do operations that are read-only, but if you want all the functions that are writing to extract it, they need an output variable, parameter. So you would create another version.
I see.
Okay. Other question? Yeah, Rosie?
Ask a question about, so your code chunk number 49, the 4th line of code, you've got gym, square brackets, gym, less than equal to close brackets, less than 1. Is that just a method of getting rid of no data, the nans?
Yes, I think indeed there were some, I don't remember by heart, but maybe some like in minus infinite values that were not really defined, like 10 to the minus 35, minus 10 to the minus 35, or some of these very strange different types of numbers, which I wanted to get rid of. So here I say all the negative values, I just want to have one negative value minus one, and I'm actually interested, and you can treat them as source no data. All negative data are not taken into account when calculating the mean and standard deviation, because otherwise I would have all this not a number in these calculations. So I say every negative value is minus one, and don't take into account this minus one when calculating these statistics.
Okay, yeah, great, thank you.
Okay. Okay, I think that was it.
Yeah.
Was nice nice working with you. It was, as I mentioned in the beginning, a very high level class. So that's nice to work with. That's fine. I hope to see at least some of you. I don't know who's coming to Matera. Would be nice to some of you in real.
Yeah, thanks, Peter. And I have one question for you, more general in terms of. So I think you are the best person to indicate us what to maintain as a, let's say, Bash, GDAL, and PK tools processing in the Bash environment, and what to do, let's say, more in the Python with PyGeo environment.
Yeah.
So can you give a sort of direction, because now we knew both that
Indeed.
most of they have an overlapping, but I think that will still something.
Yeah.
Give an indication.
Yes, I would say I'm never using PK tools again. So maybe that's already a good indication. I know you have been working with a lot, and it's a bit, it's probably a matter of what you're used to, and what you're capable, and you are used to working with Bash script. So in there, I can imagine that you want to stick with some of those. I'm not doing it. The only reason why I would say where it could be useful, if you're dealing with what, as you're doing sometimes, Giuseppe, on the cluster, like huge images, and you don't want to be bothered about splitting them in tiles, even though I implemented these tiling, automatic bit of tiling, which is the way I'm working with, to tile it and then to distribute. If you say, no, I have one big computer and I don't want to be bothered about that, I have the time to let it run, and I only have a small amount of memory, then you can use your line by line working as you were doing before. But I think in most of the cases, it is worth of taking the investment of learning how to do it in the PyGeo, because it's most of the time much faster as it is in memory. And if you have lack of memory, then you can, I'm using the tiling and then taking profit of parallelization. So I think it's the easy answer is, especially if you want to start from scratch, I would recommend to use PyGeo.
For everything, and even the standardization, because, for example, I quite often use Bash environment with the GDAL and PK tools to, let's say, to standardize all my tiling in order to avoid issues in R or in Python. And the standardization, I mean, pixel resolution and extent and so on, and entering inside Python with already well defined tiling and very matching tiles, then I can process with a powerful NumPy and so on, GPy, and all the whatever you explained. So maybe that one would be still an option, or what do you think?
I'm not sure if I understood the question. So you're trying, what you're saying is you're trying to find an example where it makes sense.
Yeah, you know, sometimes you get the satellite image or any kind of image, and you have all the different tiles, but you have pixel resolution that are not matching completely. The extent are not really square to the digit, and you have all this mismatching that I found out, for example, make a lot of problem inside R, or it's even inside Grass. Rather, if I do the standardization in the term of pixel resolution and extend, then I have my life easy in R and Grass. And I suppose also inside PyJ or all the Python.
Yes, yes. So indeed, I'm still sharing here. So what you typically can do, suppose you have
Okay, I got it. Yeah, this one will be like the digital edit.
and then you would say like, or even, and then even so I'm not sure if this is, hold on, so if this, maybe you, so you both, you have two files, diff files, one smaller and one bigger, and with one is has resolution 4.5 meters and the other has 9.7 meters, and you want to have to stack them and have the same resolution and the same bounding box. Is that your question?
Yeah, so yeah, also this one can be an
so this
example.
one, for example, so what you can do, you have you open your first image and you post this, you want, this is your reference, you want everything stacked or you mapped to this one. Then you just open your second image saying, I want to open my second image, but I want to open it in the resolution of my first image in X, the resolution the same one as my first image in Y, and the bounding box the same bounding box as my first image as well. And so after this, you end up with two images that are exactly the same and that can exactly be stacked by saying gym0 dot geometry dot stack plane gym0, as we were doing before. But now on file they were totally different in resolutions and in bounding box, and so they were not overlapping.
Yeah. This is a good example. Thank you. Perfect. So we have a question from Milutin.
Milutin.
Hi, Pete. Yeah, nice examples, and I really like this one with the tiles. And I think it's this is really a very powerful thing to go with large data. So I was thinking about actually a cloud optimized geotiffs, you know, and they are coming already with predefined tiles. So is it possible that the gym somehow is smart to already figure out those tiles and that we can like read the whole TIFF file, like just the metadata, and just read subtiles or something like that?
Yeah, it's a very good question. It's not smart like this. I haven't implemented it. It's a good suggestion. I can look into it. For now, it's not. so you would have to do it manually in the sense that you would have to check what is the, for example, with the GDAL info, you see the tiling of this, how it is tiled actually and then you would have to define those manually. But no, good thing it's not. So unfortunately, no, not smart enough. By the way, Milutin, is it possible? Do we know each other?
Yes, yeah, we know one another, yeah, from.
I was already thinking that your name and when you were starting to talk, you're from
yes,
Wageningen.
sorry, I'm working from home and a bit on sick, yeah, leave. So yeah, but I can show my face, yeah.
I see. Ciao.
Ciao. Yes, yeah. So yeah, but looking forward to discuss this because I think this cloud optimized functionalities for reading those data, this is something that can make a really difference for mixed arrays. And I also, you mentioned yesterday about these tasks and parallelization in X arrays, and it's really cool, but it's also very difficult to somehow make it working. So you have to know your data and so on. Yes. So I mean that's why I don't think that you are doing anything worse than that, because already when you prepare your own tiles, you are already somehow you have a mental picture of your data and you can easily scale it up. Yeah, that's so that's
yeah. Actually, this is also something I always say that I started all these implementations like many years ago when there was much less available, and what I see now with the whole development of what is available in X-ray, it's at a much higher level than and it's really cool what exists. And I think by, first of all, I don't say that all the work I've done has been for nothing, and I still use it today, but still there's many overlaps and things. If I had to start over, I would reuse more than what is available. Of course today that's always the case. But what also I think even one of the next steps, if I have some time, and I would really like to do, is to make use of the task functionality on how it is using this parallelization and automatic tiling and try to, as I'm using with this going back and forth between PyGeo and X-ray, is when one of the difficulties with X-ray is that there's a number of functions that are already implemented to do it with task, but not all of them. And so what I would like to do is to interfere when it's doing this parallelization. You can also ask for the smaller array, the tile that it is using internally, interfere there and working on that tile with PyGeo, so that I can use all the functionality from PyGeo and then give back that the result as a new tile for X-array, so that that makes like the whole circle complete, because for now I'm using X-array, but only the part of X-array that is entirely in memory, but not so far the tiling internal tiling mechanism that is very powerful of X-array. And once that would be done, that I think that would be very neat, and I think it's possible, but it would take some time.
Yeah, that's that would be a cool addition. Yeah, but just add on that. Take care, you know, for example, this rolling thing requires different task structure than, for example, spatial rolling. Yeah, so if we do temporal spatial rolling, so then we need to retask everything. Yeah,
yes.
And so that's the very important thing, and usually the most confusing part of that.
Yes, yeah, good point. Yeah, no, it can be quite daunting indeed.
Yeah. Thank you.
Yeah, welcome.
Yeah, thanks for the brainstorming on the parallelization of GIMP and Dask and so on. We will have more time to go deep in this kind of brainstorming in Matera. So Pieter is coming, so it will be occasion to talk directly with him with a nice beer your food.
Do we know how many people are coming to Matera?
They are like 12 or 14. So, but I'm waiting a few more. So if somebody changes his mind.
So I will be there on what was it,
From Sunday to Wednesday.
on Sunday evening, and I will be leaving. I think what was
Wednesday.
it on Wednesday? Yeah.
I think on Wednesday.
Yeah.
Yeah. Or maybe Thursday. Yeah.
Yeah. So yeah, I would suggest, I don't know how many of the ones that are coming are so here today, but I would really suggest to make the most of the time we have there together by preparing some things, and maybe also in advance show you if you're working on some things. We can share some ideas of some files. If you have some problems, we can also, I mean, you don't have to do it in advance, we can also do it there. But I think that the nice thing of being there together is that we can really work on some data rather than me giving another presentation. I can do it, but I think it's much more interesting if we can work on some real data of your data, in which your the problems you have, what you would like to do, what is possible, what not. I think that's where the real nice thing about collaborating, and when we see each other in real life, it's better.
Yes, indeed, and this is the case of the Matera is more an hackathon week than not a lecturing. Maybe it can be a short talk or half an hour or some topics that is interesting for everybody. Okay. Thank you very much, Peter. And concerning our rolling time, next week is going to start in the machine learning. So don't forget all these data preparation and data processing for the geo environment, raster and vector format with Bash, with Python, with all the different flavor. And then we will enter with Antonio for the machine learning. So I encourage also Peter to follow, because Antonio is very geek on this. So tuning your brain and get ready for more coding, and we see next week the usual, now Wednesday and Friday.